sensitivity analysis. Is the following, right? You are given the system of equations Ax is equal to B. And we realize that every time you cannot have B exactly given or A exactly given. So we consider the case Ax hat is equal to B plus delta B. Or in other words, so you can say that A into x plus delta x is equal to b plus delta b, right? And then we thought if this delta b, the perturbation is small, then can we give a condition? Can you give a bound on when the perturbation delta x is smaller? So in other words, perturbation in x, how is it affected by perturbation in b? Can we give some results, right? That's what we were trying to investigate. One thing to remember here is that because delta b is perturbed, it is bound to happen that x will also get perturbed no matter what, right? So there will be some perturbation in x. How big that perturbation is x is with respect to x, given that perturbation in b with delta b with respect to b is small. That's what we were trying to investigate, and we arrived at a result yesterday, right? We did some manipulations and we arrived at this particular result, right? Less than or equal to norm of A into norm of A inverse delta B by B, correct? So this is the result at which we arrived. And this is your first sensitivity analysis result, right? So this was sensitivity analysis result. Here, this particular number was called as condition number of the matrix A, right? This is the condition number of matrix A. Obviously, A is square system and A is invertible. Okay, that's what we had assumed before the start. Okay, so this for some time now, we'll assume this, and then we will relax these conditions. Okay, later on we'll relax these conditions, and still we'll be able to achieve results which are similar to this. Okay, so for the time being, we are assuming this. So let us consider that A square, A is invertible, and then you get this first sensitivity analysis result. So what does it really mean? It means that if condition number of A, okay, so if condition number of A, which is defined as 2 norm of A into 2 norm of A inverse, is small, okay. So we do not know what is small is, but if it is small, then delta B by B small, meaning that you have a very small perturbation, small relative perturbation in B. This implies that perturbation in A, perturbation in X is also small, right? So this is a qualitative statement. This qualitative statement is actually being derived from this particular numerical result, right? So this is the quantitative statement, and this quantitative statement helps us to make certain claims, like if condition number is small, then small perturbation in B results in small perturbation in X, right? So this is a qualitative statement that I am making, and this means this really means that the solution is not sensitive in this case. The solution is not sensitive in this case to perturbations in B. Correct? So solution is not very sensitive because X is only slightly ever-changing, right? So it is not sensitive to perturbations in B. That's what we see. But on the other hand, if this condition number is large, okay. So on the other hand, if condition number of A is large, okay, so again, what is this small, what is large, we don't know, but let us see. So condition number of A is large, then what can we say? Okay, so condition number of A is large, then small perturbations delta B by B may not result in or may result, okay, the better way to write is that they may result in relatively large perturbations, okay, large perturbations, delta x by x, correct? So this actually happens. See the example we discussed earlier, right? Okay, so in that case, we'll have to compute the condition number of A. So I'll calculate the condition number of A and then we can refer to that example. But refer to the example we discussed. Okay. We will calculate condition number of A. Where A is equal to this. Okay, we will do that. And we will see that the condition number is really very large, and that results in this type of problem. Not always though, okay, you have to remember that we are having an inequality here, and in that inequality you saw that not every perturbation delta B results in a very large perturbation delta X. If you see, that's why specifically that example was taken. I think do we have that example in yesterday's class? Unfortunately, no. But I think you remember, right? So this result that you obtain, not every perturbation actually will give rise to a very large perturbation in X. But there are certain specific perturbations which will really blow up this X plus delta X. Okay, so that is something that needs to be understood. So, so the way we'll summarize this situation is that this means the solution X is, or we can say the solution X may be very sensitive to small perturbations in, so small perturbations delta. So so this is what this particular statement is saying. So once we understand this that this is what is really happening, then it becomes clear why we really are interested in something like condition number of A, right? So this condition number of A is scaling. So a good way of using this result is that a matrix A with which you start has a small condition number, then you are guaranteed that small perturbations in B are not going to affect X very much, right? Your X is not going to very much. But if the condition number is large, then small perturbations in B may affect perturbations in X to a very large degree, right? So that is something that really is very important, and we have to understand what is really happening. Another important thing is that even if the condition number of the matrix is really high, is it really a bad thing or not? That is also something that we need to discuss. So it's a like it's nothing like this condition number is good and this condition number is bad. Okay, so first let us understand what is the range of condition number. Okay, what is the range of condition number? So for example, what value condition number may take and how good that condition number is, and so on and so forth. So the first thing that you notice is that what is condition number of identity matrix? So condition number of identity matrix is 2 norm of identity matrix times 2 norm of inverse of identity matrix, which is same as 2 norm of identity matrix, 2 norm of identity matrix, which is equal to 1. Because identity matrix has 2 norm 1, you all saw that. You remember how do you define maximum X not equal to 0 norm of Ix divided by norm of X. That is nothing but identity matrix 2 norm, right? That is the calculation. So this will be equal to maximum x not equal to 0, norm x by norm x, which is 1, which is equal to 1. So the 2 norm of identity matrix is 1. Simple calculation. We saw this yesterday. So the identity matrix is norm 1. Then what do I start with? So for any matrix A or for any invertible matrix A, for any invertible matrix A in Rn by n, we note that identity is equal to A inverse, right? Identity is equal to A inverse, which implies that 2 norm of identity matrix is nothing but A inverse 2 norm. So I will write this as 1 is equal to 2 norm of identity matrix is equal to A inverse 2 norm. And what can I write down this as? I can write this down as norm of A into norm of A inverse. This is because of submultiplicative property. And what is this actually? This is nothing but condition number of A. So what do we get? We get that condition number of A is always greater than or equal to 1. Correct? So the best possible value of condition number is 1. And surprisingly or not surprisingly, all orthogonal matrices exhibit condition number to be equal to 1. So amazing property, right? So the best possible condition number is possessed by the orthogonal matrices. And now you will start realizing why these orthogonal matrices play a very important role, why people always make so much fuss about using orthogonal matrices. One of the reasons is that the condition number of those orthogonal matrices is 1. Okay, so this says that best possible condition number is 1. Correct? So best possible meaning the smallest value, and condition number is always greater than or equal to 1. So you can start with 1 and you can go on all the way up to like infinity. Like any real number as large as possible you can think of will be a condition number, right? But the smallest one is 1. Note that orthogonal matrices have best possible condition number. So orthogonal matrices have best possible condition number. So now come back to this particular result once again. So this is the result that we stated, and the best possible value of condition number is 1. So if you started with a matrix A and you are trying to solve Ax is equal to B, if the condition number of the matrix is 1, okay, so you have best possible condition number available there. So if the condition number is 1, then what is this sensitivity analysis result really telling us? The sensitivity analysis result is actually telling us that you see this condition number is 1. So the error in X is at least as much as error in B. Okay, so that is reasonable thing to assume. You started with error in B, then you expect at least as much error in X as there was in B relatively. Okay, so that's what this statement is saying in best possible case. And if condition number of A is not 1, then we now know that condition number is always greater than or equal to 1. That means that condition number can take values which are really very big, like 10, 100, 1000 and so on and so forth. So you are scaling the error in B, and you are saying that error in X gets magnified or it gets scaled up by that condition number factor times the relative error in B, right? So the best possible scenario is the relative error in B is relative error in X is at least as much as relative error in B. That's the best possible case, right? Condition number of A is 1. So this result, if you start looking at it from all these different points of views, then this result starts making sense to you, right? So this result starts making sense to you, and the best way to understand this result, the best way, can you say, Kshitish, what do you mean to say?
So you were saying that like in the best possible scenario for a condition number, the relative error in X is at least that in relative error in B. should we
No,
at
relative
most
error
write
in X, relative error in X is at most relative error in B. Okay. So, so, so there is some error in B, at most that much error in X also you will observe, relative error. Okay. That is what we are raising. Did I say at least? Maybe I was wrong. Okay. If I said at least, I was wrong. So, okay, I will say it again. B is erroneous. So you expect there is an error in X, and you are saying that error in X is at most as much as that in B. That's what this statement is really saying. Does that make sense, Kshitij?
Yes, sir.
Yeah. So I meant this. If while speaking I said something else, I'm sorry. Maybe that was wrong. But this is the meaning. So that's what I really mean. Okay. So this is the condition number, and this is about some sensitivity results, right? So, oops. So now what? Okay. Maybe I need to start sharing. So what we want to see now, is that we want to see the geometrical meaning of this condition number. Okay, and try to understand what these things are geometrically really doing. Okay, so once we start the geometry, the picture becomes even more clearer. Okay, it becomes even more interesting. You will see geometry helps us understand things very nicely. So let us go and look at what is happening geometrically. Okay. Geometrical interpretation. Okay, so that is what we will look at. So this geometrical interpretation, once again, there are two things that I'll look at. Okay, so condition number of A is basically defined as 2 norm of A into 2 norm of A inverse. Correct? That's how I define condition number of A. 2 norm of A into 2 norm of A inverse. So first let us understand what is the geometrical meaning of 2 norm of A. But that somehow we already know, right? What are we looking at? You are looking at maximum magnification that this actually induced, right? So this is what you are really looking at, maximum magnification that this guy induced. One thing that you can look at, so this is how you will define 2 norm of A. So one calculation, simple calculation you can check is that I can write this down as A into X by norm X. Can I write this down like this? What property I have used? What property I have used of norms? So you can consider alpha is equal to norm of X, right? If you consider, then what do you have? This statement really is maximum X not equal to 0, norm of Ax divided by alpha, correct? And that alpha being scalar, I can take inside. So maximum of X not equal to 0. You have A, sorry, I will do one more step. So this is basically 1 by alpha Ax, correct? And A is a linear transformation, so I can write down this X not equal to 0, A X by alpha, and that is what I have written here. But this is happening for any arbitrary X, right? This is happening for any arbitrary X. So this is true for any X not equal to 0. X by norm X is a unit norm vector. You are dividing by the norm, right? You are dividing by the norm. So X by norm X is a unit norm vector for any X not equal to 0. So this I can write down. So 2 norm of A, which is nothing but maximum of X not equal to 0, norm of Ax by norm of X. I can write this down as maximum of X not equal to 0, norm of X by 2 norm of X. which is same as maximum norm of y is equal to 1 ay. I can write it down in this way also. Is that clear? Is that clear? So what I am really looking at, is I can look at this, and I can write it in this particular fashion. Okay. So this is another way. In which you can define this induced norm. And now we will see geometrically what it really means. Okay. So we'll see geometrically what it really means. The reason why I did this calculation is that it becomes easy for me to understand geometrically what is really happening. So first I'll define something which is called as maximum magnification. Okay, maximum magnification. Okay, so I'll write down max A is equal to maximum x not equal to 0 norm of ax divided by norm of x, and we saw that this I can actually write down as maximum norm of so I can just write down x also if you are okay. Is that fine? So this second part is actually going to enable us to visualize geometrically what is really happening. And the way I define maximum magnification, I can define minimum magnification also. So minimum magnification of A. Okay, minimum magnification of A. What is going to happen? Minimum magnification of A is, instead of maximum, I look at minimum. Norm of Ax, it's 2 norm divided by 2 norm, and similarly you can show that this is equal to minimum. So again, this is something that we will use to understand geometrically. Are these two definitions clear? Straightforward, right? We have working with maximum magnification. So by definition you can see, that by definition 2 norm of A is basically maximum magnification of A, correct? 2 norm of A is basically maximum magnification of A. So what is 2 norm really measuring? 2 norm is measuring how much maximum magnification you can get, right? So similarly, minimum magnification we are defining. So you look at all the vectors, non-zero vectors. You see what is the action of A on those non-zero vectors and how does the length scale. So the length may go up, the length may go down, right? Length may go up, length may go down. So what is the smallest length to which A scales x to? That's what you are really looking at. That's the minimum magnification, right? As exactly opposite to the maximum magnification. So one straightforward thing that you can tell here is that what is the minimum magnification for orthogonal matrices? What was the maximum magnification for orthogonal matrices? Both will be equal to 1, right? So maximum magnification, minimum magnification, both of them are equal to 1 in case of orthogonal matrices. Why? Because we have already said that orthogonal matrices do not change the length of the vectors. If you have a vector x, then you see the action of q on x, which is nothing but qx, and you see that length of qx is actually same as length of x, right? So if the length of qx is exactly same as length of x, then there is no magnification or like maximum or minimum to worry about, right? The lengths are preserved. So minimum magnification is also 1, maximum magnification is also 1, and condition number is also 1, right? So these things seem to be related. Okay, so these things indeed are related, and this is what we are going to investigate. How can you relate condition number of a matrix with these maximum and minimum magnifications and what is really happening? Okay, so note, for orthogonal matrices, for orthogonal matrices, maximum magnification of Q as well as minimum magnification of Q. Both of them are 1, right? So this is what we observe. Orthogonal matrices really very well behaved. Okay, so let us see what is happening now. Okay, so A is a map from Rn to Rn, right? I am considering a matrix A in Rn by n invertible. I am talking of this class. So this is what we have, right? This is what we have. A is a matrix from Rn to Rn, and it is invertible. And once you have such a matrix A, you can view of it as a linear transformation, right? So every x in Rn is being sent to Ax. Correct? That's where this thing is really going, right? So for example, I take n is equal to 2. Okay, n is equal to 2 is always easy to understand. N is equal to 2 is always easy to understand. So I will take n is equal to 2. So every vector x1, x2 goes to A times x1, x2. Correct? So this is basically A11 x1 plus A12 x2 and A21 x1 plus A22 x2. Okay. This is what you have. And now what I am really going to look at is I am trying to understand what is the minimum and maximum magnification. Okay, what is minimum and maximum magnification? So you see, what is maximum magnification? Maximum magnification, I will use this second equivalent definition. So what am I really going to look at? What I am really going to look at is the unit circle or unit ball in the domain space, and I'm going to apply A on each of these vectors, Ax, and I'm going to measure the length of each of those Ax, and whichever is the maximum length, I'm going to work with that maximum length, right? So first business, draw a unit ball, right? So this is a unit circle, unit ball. Okay. So this is unit ball or unit circle. What is this? 2 norm of x is equal to 1, right? So this is what it is. And now I apply A on each of these vectors, right? So there are like these vectors. This is one vector. This is another vector. There are like infinitely many vectors on this unit ball. I'll apply A to each of these and see where does they go to, right? So they may go in different directions, different places. So what really happens, I'm going to draw directly and then you can see. Okay, so this circle under A actually gets mapped to an ellipse. This circle gets mapped to an ellipse. Okay, and this ellipse is a very very interesting ellipse. Okay, so this is the ellipse to which this circle gets mapped to. So the first question that you can ask is, why will it get mapped to ellipse? So can anybody tell why will it get mapped to an ellipse? So this is the major axis of the ellipse. This is the minor axis, right? So yeah.
The norm of a vector and its negative is same. So the mapping that A does for one vector would be the distance from the origin would be the same of the negative vector also. So that's why the symmetry will be maintained, but then you are stretching some of the parts more and stretching some of the parts less, so it will become an ellipse.
It could have been a parallelogram, right? Like parallelogram. It could have been a nice parallelogram. Why it has to be an ellipse and no other diagram? It could have been something like this here, and the same, to maintain symmetry, I draw it like this. It could have been a figure like this also, no? Why is it not a figure like this and an ellipse only? Why it does not become something like this? Look at this coordinate, look at this and this. These are the coordinates. You have the constraint that x1 square plus x2 square is equal to 1. So using these constraints and using these coordinates, if you want to check the norm of this vector, what will be the figure? Remember your 12th standard coordinate geometry equations of ellipse. If you want to understand easily, so I am not going to give the answer to this. This is something that you have to find out. You can try different A's. Okay, so this I will put in the next assignment also, but you can try different A's. So at this point of time, you take on face value. Okay, I want you to investigate this. We'll discuss it in the next week once again. But I want you to take this on the face value that a circle will go to ellipse, for example, at the point of this time. So if a circle is going to ellipse, this is the major axis, this is the minor axis. What is the maximum magnification? Okay, so what is really happening? There is this vector here. This vector gets mapped to this particular vector, right? Then there is another vector here. So this vector maybe gets mapped to this particular vector. Okay. Then there is another vector, say this vector gets mapped to this particular vector, and so on and so forth, right? And then there is this vector, maybe that this vector gets mapped to this vector. Okay. So this green and blue, fluorescent blue, right? These are the two vectors that are really very important to us, right? So you see the mapping, right? The mapping is this vector is going to this vector, and this vector is okay. So this blue one is going to this blue one, right? So this is the mapping that is happening. And clearly, what is the maximum magnification? Maximum magnification, do you all agree, is this particular length, half length of major axis? And what is minimum magnification? Minimum magnification is half length of minor axis. So geometrically, maximum magnification half length of the major axis, and minimum magnification half length of the minor axis.
Sir?
Yes?
Sir, we can equate this to y1 and y2.
Yeah.
Then we'll get two equations in x1 and x2. So, so like if we solve, we know that x1 square plus x2 square is equal to 1.
Correct.
So if we find an equation with y, by substituting that, you'll get like y1 square by some a plus y2
Correct.
square by some b is equal to 1. So that is an ellipse.
That is an ellipse. Absolutely right. So that's what you're supposed to do.
Yes,
absolutely
sir.
Right. That's why you will always get an ellipse. And the same analogy you can extend for Rn to Rn, and then you will have a unit sphere, so to speak. In R3, you will have a sphere, and that sphere will get mapped to an ellipsoid. And in the dimension beyond 3, I cannot even visualize, but you will have a unit sphere, and that will get mapped to a unit ellipsoid. Okay, so, to an ellipsoid, not unit. It will get mapped to certain ellipsoid. But you can convince yourself, right? So yeah, good job, Aditya. So that's what we really are interested in. So a circle will get mapped to an ellipse, right? That's what will happen. And geometrically, clearly, what is the maximum magnification? Maximum magnification is basically the highest length in the ellipse. What is the highest length in the ellipse? Highest length obviously is along the major axis. So the vector, so the highest length is basically half length of the major axis. That is the maximum magnification. So that is the maximum distortion that can happen to this unit circle. So what is really happening? You have a unit circle, and unit circle is getting distorted, right? So that's what you are seeing. And maximum magnification is there, minimum magnification is there, and they very nicely you can see along the major axis and minor axis of the ellipse. That's what will happen. So geometrically, this is fitting very beautifully. Okay, now at least one student in the class, Aditya, is it? So Aditya has already proved that it's an ellipse. So you can all try yourselves and you can see that you will indeed get an ellipse. Okay, so let us take a simple example. Okay, so let us take a simple example. Suppose this is the matrix A that I get. Suppose this is the matrix A that I get. Now, can you tell me what will happen to the unit sphere, unit circle? So I have a unit circle. Now you apply A on every point in the unit circle. What is the ellipse that you are going to get? Can you tell me? So what is the action? Action is AX is basically equal to 0, 1, 0.1, 0 into x1, x2 is equal to what? You will get x2 and 0.1 x1, right? And you know that x1 square plus x2 square is equal to 1. So what is the ellipse that you will get? Will you get an ellipse like this? Am I right?
Yes, sir. 10 times major axis, 10 times.
Yeah, major axis is 10 times the minor axis. This is the ellipse that I will get, right? And the major axis is along the y-axis and minor axis of this ellipse is along the x-axis. That is how it is going to work. And this distance I know is 0.1. Am I right? No, it is half of 0.1, is it? So 0.1 by 2 and this distance is 10 by 2, right? Half of it I am really taking. So this is 5 and 0.05, right? The ratio remains the same. That's not a problem. Is that okay? Do you all agree?
It will be 0.1. This is a x square upon a square.
Yeah, but that 0.1 will be this entire thing, right? Length of minor axis. I'm taking only half of it.
The length of minor axis is 2b.
Okay, so let me get it right. So I have forgotten my coordinate geometry. So what is this distance? So what is maximum magnification? What is this length?
This is 1.
This is 1, correct. And if this is 1, what is this length?
0.1.
0.1. Okay, that's fine. It suits me. So this is what you have, right? The ellipse will look like this. And in fact, from this diagram, because this A is very easy, A is very simple to understand. What is the vector? So this is the vector here. This is the vector here, which is the maximum magnification. So the direction of maximum magnification is y-axis, and the minimum magnification direction is x-axis, right here. But which vector is getting mapped to this minimum magnification direction? And so here what is happening to E1? So this is your E1 vector. Where is E1 getting mapped to? And where is E2 getting mapped? So AE1 is equal to what? And AE2 is equal to what? What is AE1? And what is AE2?
0,1 and AE2 0.1, 0.
0, and this is 0,1, right? So basically E1 is going to this vector, right? So this I will make it blue. So E1 is going to this vector and E2 is going to the vector on the x-axis, right? So what you really observe here is that in this domain, so this is the domain space and this is the range space. So in the domain, which direction corresponds to the direction of maximum magnification? So this is the direction, right? Even direction. So the direction along the x-axis is the direction of maximum magnification, because vector in that direction is getting magnified, while the vector in the direction of y-axis in the domain is like shrink. It is getting in the direction of minimum magnification. So do you understand what is really happening? It's basically a rotator, right? And that rotation is not plain rotation. I am twisting that rotation little bit, right? Basically, that's what is happening. So this is what geometrically you see is really happening. And now I can play with this a bit. And you see this play is really very interesting. Okay, so here instead of 0.1, I put a alpha. Okay, alpha is not equal to 0. I put a alpha is not equal to 0. So if I put a alpha here, then you see everywhere at important places where 0.1 appears, I will have a alpha here, right? I will have a alpha. And more importantly, I will need this AE2, so I will write it down neatly once again as alpha 0. Okay. And now you tell me what is the game I am going to play with this alpha. Suppose I take alpha is equal to 1. What happens to the unit circle? If I take alpha is equal to 1, what happens to the unit circle? Unit circle gets mapped to the unit circle. Do you agree?
Yes, sir. Yes.
Now, if I take alpha to be positive only, okay, for the time being, I'll take alpha to be positive. It doesn't matter. I can take negative value of alpha also, but just to understand. Now, if I take this alpha to go to 0 from positive side, okay, if I take this alpha to go to 0 from positive side, I am taking alpha greater than 0. So suppose I take alpha is equal to 0 point, the way I have it in this diagram done, then this unit circle is going to a ellipse, right? And the ellipse is really very elongated. The ellipse is really very elongated with the condition that the major axis of the ellipse is 10 times bigger than the minor axis of the ellipse. Basically, alpha times bigger than the minor axis of the ellipse. Right? Now, if I take this alpha to be equal to 50, what 0.5? Sorry, 0.05. Okay, what will happen? The ellipse will become even more elongated. Do you agree? Ellipse will become even more elongated. If I take alpha a very small number, what will happen? The ellipse will really be very elongated ellipse. The ellipse will be really very elongated ellipse. It will almost start resembling a line segment. Do you agree? It will almost start resembling to a line segment on y-axis. That's what will happen. On the other hand, if I take alpha to be greater than 1, suppose I take alpha is equal to 10, then what will happen? If I take alpha is equal to 10, what will happen? I will have an ellipse, but it will be fatter now, right? And if I take alpha is equal to 1000, I will still have an ellipse, but much fatter, right? So the ellipse will be like very elongated along the x direction if alpha is positive going to infinity. And if alpha is positive and going to 0, I have a very elongated ellipse. The ellipse, the way it is getting elongated is between that +1 and -1. It starts shrinking, and it almost becomes that line segment on the y-axis between -1 to 1. You see this game, what is happening with this alpha and how the circle gets deformed and it gets into that ellipse. Do you see this game geometrically? Is there any doubt?
Sir,
Yes.
I just wanted to clarify one thing.
Yeah.
So here E1 when we'll take, so in that case X1 will be like 1 and X2 will be 0, right?
E1 is this vector 1 0 and E2 is this 0 1. Standard unit vectors, our standard.
So sir,
So sir, it will be,
AE1
the ellipse will be like 90 degrees of.
No, so did I make a mistake in diagram?
Yeah, sir. Like we will always have the like one like we will have the ellipse. The maximum points of the ellipse on the x-axis will be 1 and -1, and the ellipse will basically stretch across the like y-axis.
Oh, you should have told this to me before. So this is wrong ellipse, you are saying? I should draw it like this?
Yes, sir. Like sir, in the AE1 result, it should be 0 alpha.
It will be 0 alpha and this will be 1
And this
0.
would be 1 0. Yep.
Are you sure? Now I'm not doing calculation. I'm trusting you. Okay. So I trusted previously Ramnivas and Aviraj.
Yes, sir. This is right.
So you see the ellipse is like this. Is that right? Is that right? This is how the ellipse will look like.
Yes, sir.
Aviraj,
Yes, sir.
क्या correct है? Aviraj, is this correct or not?
I'll have to see, sir.
सर मैं कुछ गलत नहीं बोला था, ये अविराज था.
Okay, no problem. आप दिमाग से गलत नहीं बोला. But figure कैसा है? You tell me the figure of the ellipse. How will the ellipse look like? So A E1 कहाँ जा रहा है भैया? ठीक से करो calculation. Where is A E1 going?
Sir, x-axis is major axis.
X-axis is major axis. Okay. तो मैंने जो figure निकाला था वो गलत था. This is fine. X-axis is major.
X-axis is major axis when alpha is less than 1.
Yeah, that's okay. So we are taking alpha less than 1 for the time being. We are not really worried. Okay, so you take alpha less than 1 for the time being. That's okay. No problem. So this is how the ellipse will really look like. So this will be 1, this will be -1. You will have alpha here, you will have minus alpha here. Correct? That's how it will look like. And this is the length of major axis, half major axis. This is the length of half minor axis. So this is your maximum magnification and this is your minimum magnification, right? All other discussion that we had is same, except for the fact that if you now take alpha to go to 0, then what is going to happen? This ellipse is going to start collapsing and it will collapse onto the x-axis, right? It will collapse onto the x-axis. Do you agree? All that discussion remains same. Instead of I said it will fall onto y-axis, now you see it will fall onto x-axis. And if your alpha is greater than 1, then your ellipse will start getting elongated. So y-axis will become the major axis in that case, and it will be elongated. And you see it will be a very big ellipse, -1, 1 fixed on the x-axis. So it has to go through those 2 points, and big points alpha and minus alpha there on top, and that's how the ellipse will. And you take alpha to infinity, you will really stretch it out. Really stretch it out, it will still go between -1 and 1, and that is what is going to happen. Do you understand the geometry? Do you understand the fun in this figure? Now let us try to relate the concepts that we have learned so far with this figure. Okay, so when you take alpha to go to 0, what is really happening? What is really happening between the vectors when you take the alpha to go to 0? If alpha were equal to 0, in this particular case, you take alpha were equal to 0, what would happen? What would happen to the circle?
Line.
It will become a line segment, not line. Alpha, so the circle will become a line segment and it will be a line segment between -1 to 1 on the x-axis. Do you all agree? And what is the vector E2 here representing them? What is the vector E2 here representing them? And what is the vector E1 here representing? So you see, where is vector E1 going? It is going to AE1, which is nothing but 0 and alpha, right? So E1 is the direction which is going to 0 alpha direction. If I took alpha is equal to 0, then E1 is going to 0, 0. That means that vector E1 is in the null space of the matrix. If I take alpha is equal to 0, then E1 is a vector which is in the null space, right? So right now E1 is the vector which is giving me the direction of minimum magnification. That minimum magnification is alpha in this particular case. And if I take that minimum magnification alpha to go to 0, then E1 is kind of giving me the direction that probably is the direction of the null space of the matrix A. Do you understand where we are going with this? And again, you think of what orthogonal matrices are doing. What orthogonal matrices are doing, because maximum magnification is 1, minimum magnification is also 1 in case of orthogonal matrices. A unit circle is going to unit circle. So the orthogonal matrices are sending unit circles to unit circles, and all other matrices are sending circles to ellipses. The ellipses might be good ellipses in the sense that they are not far too stretched, right? They are not too much elongated, they are not degenerate. But if certain matrices are such, that you see a circle is going almost to a line segment, not exactly a line segment, but very degenerate ellipse, then that is something that is not something which you will like. What is happening? You are really looking at ratio of maximum magnification to minimum magnification, and based on that ratio of maximum magnification to minimum magnification, what you can really see is that how bad the shape of circle becomes when it becomes an ellipse. How much is the distortion that happens to the circle when it becomes an ellipse? If the ratio of maximum magnification to the minimum magnification is not much, if the maximum magnification is same as minimum magnification, for example, then circle will be circle. But minimum magnification is always less than or equal to maximum magnification. So this ratio of maximum magnification to minimum magnification is always greater than or equal to 1. Closer this ratio to 1, less is the distortion to the circle. Highest the ratio, like as you increase this ratio, then there is more and more distortion. The ellipse becomes really prominent. What other number was always greater than or equal to 1? We just saw what number was greater than or equal to 1 always, and best possible case it was 1. You are looking at a ratio here which is maximum magnification by minimum magnification, and this ratio of maximum magnification to minimum magnification is always greater than or equal to 1. What was other number that we saw in this lecture is always greater than or equal to 1?
Condition number.
So can we now relate these two things? At least at the outset, it seems that these two numbers have same range. The ratio of maximum to minimum magnification and condition number. In fact, what we will show, not unfortunately today because time is up, is that condition number is actually equal to this ratio, maximum magnification of A divided by minimum magnification of A. We'll actually prove that condition number is this particular ratio. And once you understand this, then what we are only looking at is that how this circle, unit circle, becomes an ellipse and how bad this ellipse is. Bad in the sense that what is the maximum magnification to minimum magnification ratio. Okay, once you understand this geometry, you can take this understanding to higher dimensions like R3 to R3, R4 to R4. It's same, you have an ellipse, you have a sphere, unit sphere, and how bad that unit sphere becomes when you act A on that unit sphere. So it will become an ellipsoid. Why it becomes an ellipsoid? Aditya already showed why it becomes an ellipse. Same logic, we will see it becomes an ellipsoid. So you continue this and you see how much the shape changes from a regular shape, unit norm sphere, to this irregular shape, an ellipsoid, right? How bad that irregularity happens. That is basically is measured by the condition number of the matrix, maximum magnification to the minimum magnification. That will exactly be the condition number of matrix A. So now you think of it, a matrix A which distorts this unit sphere extremely badly, that matrix will have a problem with sensitivity also. See, all these things have to be related, right? So this matrix will have problem with sensitivity also, because we are saying that if you have bad condition number is really very large condition number in some sense is bad condition number. So if the condition number is really large, then the matrix is susceptible, then the sensitivity is going to come into picture big time. Small perturbations in B are really going to affect perturbations in X possibly, right? That's what we have seen, and condition number determines that. And geometrically, what is this condition number? Geometrically, this condition number is basically how bad this distortion happens to the circle, right? So bad condition number is condition number where maximum magnification to minimum magnification is really very large. Okay, so these are some concepts that I have like floated around today, and we want to very nicely connect these concepts together. And once we understand this, if you understand this, then you already understand singular value decomposition geometrically. And if you understand singular value decomposition geometrically, then you understand principal component analysis also geometrically. And once you understand that, then all these things very nicely fit in together. Okay, we can understand the sensitivity and all these things together very nicely. Okay, so this is a lot to digest. So a lot of things to verify also. Main is like why circle will go to ellipse. Convince yourself, all of you, and then understand this minimum and maximum magnification. Really sorry, I have paid attention when I was drawing this figure. So thanks Kshitij and others to pointing this out, that the ellipse should really look like this. Okay, so this is something that I do with today. Next week we'll continue this discussion. Tomorrow we'll have class test. Okay, so the way class test is going to happen, you will have to submit the class test in MS Teams. So tomorrow at the end of the start, you will see that there is some submission like assignment you might have checked in. This quiz is open. I will give full 2 hours, even though I believe that it requires only half an hour to solve the class test. I'll give full 2 hours. Some questions are like fill in the blanks and multiple choice type of questions, and there are some questions which require you to write the answer properly. So again, what you are supposed to do is you write the answer properly, take a photo and just upload the PDF or like whatever the instructions. At each question you will have a place to upload the file if you are required to upload the file. And what file you have to upload, write down properly the answer and just upload that as PDF or image. Okay, so that's what you're supposed to do. So for that you will have to be prepared, and for that same reason I'm going to give you 2 full hours, because you may have problem of internet speed and all those things, and the files are not getting uploaded and all that stuff. But because I believe that that quiz can be done in half an hour, and I'm giving you 2 hours, there will be no extension beyond 2 hours. Okay, so within that time, for all the things like internet connectivity speed, you are not able to upload and all that stuff, you have to take care of it yourself. And you have to understand that towards the end of the quiz, there is a lot of activity in uploading, so server may get slowed down and all that stuff. So don't wait until the end of 2 hours to upload all your answers. As soon as you finish, you upload. Okay, so that's what I will recommend. So
Syllabus till today started?
Syllabus until last Friday.
Okay, thank you.
Okay, thank you. All the best and see you
Sir?
tomorrow. Yeah.
We will
Yes.
get question from MS Team.
Yeah. For your convenience,
Okay,
I
sir.
am
Thank
also
you.